Hello, and welcome to Agrosive Physics. Today is day 136, and what we're going to do is discuss the classification of matter. Now, we talked about quarks yesterday and the 6 flavors: up, down, charm, strange, top, and bottom. And what I'd like to do today is discuss how matter is broken up into different categories. In our reference table, we actually have a chart of subatomic particles and how they're broken down. It's almost a flow chart, if you will. And what we have is 2 different types. We have the hadron and we have the lepton. Now, a hadron is something that lives in the nucleus. It's affected by the nuclear force. So the hadron is something that you need to know is in a nucleus. Well, we know neutrons and protons are in the nucleus. So hadrons are typically protons and neutrons. But other things can exist inside the nucleus as well. Leptons, on the other hand, exist outside the nucleus. Now, the most common that we know of is the electron. But there are particles being discovered almost daily that also exist outside the nucleus. And some examples are the meson and the electron neutrino and the tau particle and the tau neutrino. And all of these particles are really cutting edge of science. All you're responsible for knowing is that they exist outside the nucleus. So that means they're not affected by the strong force. They're not affected by nuclear forces. You're also given on a chart values of leptons and what their charges are. So even if you don't know what a particle is, in fact, that there may be particles that we're discovering today, what you're responsible for knowing is where do they fit in this taxonomic chart, if you will, of matter. So hadrons are inside the nucleus and leptons are outside the nucleus. That's the first thing. The second thing is hadrons are broken up into 2 parts as well: the baryons and the mesons. Now, the baryons are heavy particles that will decay, and they're always made of 3 quarks. So the baryons have a flow chart down to the 3 quarks on the reference table. The mesons are made of a quark and an antiquark set. Now, what's an antiquark? Well, something I haven't mentioned before, because it's really something that's almost sounds science fiction-esque, is that there's antimatter. Every particle has an antiparticle that's associated to it. And what we're responsible for knowing in this course is that the antiparticle is going to have an opposite charge. So an electron has an opposite particle called the positron. And instead of having a negative charge, it has a positive charge. But it's not a proton. It's an anti-electron. Now, the way we denote antiparticles is we put a line over them. So we can actually have antiquarks. And the antiquarks will have a negative sign instead of their original. So, for example, an anti-up, which means it's a U with a line over top, is going to have a negative 2/3 charge. Now, antimatter and matter don't like each other. And when they collide, they release energy. But let's get back to the different types of hadrons. The other type is a meson. And they are stable. They don't decay. But they're made up of a quark and an anti-quark. And they are building blocks that make even larger particles. And we're finding out about new particles, it seems, weekly. Now, that's something that you can study as you continue your journey of physics in college and beyond. Maybe you'll get to work in a lab someday. Maybe you'll get to work with a particle accelerator and discover new particles that we don't even know about. Right now, though, in order to pass your state assessment this year, you're going to need to know that a baryon is made of 3 quarks and that a meson is made up of a quark and an antiquark. But they can't be made up of the same quark and antiquark because they're going to annihilate one another. In fact, the other chart that we have for classification matter is leptons. And the leptons I mentioned before live outside the nucleus. Leptons, like electrons, the meson, the electron neutrino, the meson neutrino, the tau neutrino, and the tau particle all have different symbols listed on the reference table and all have different charges. Neutrinos obviously are neutral. They also have no mass, so they're very odd particles in and of themselves. And then the tau has a negative 1 charge. Now, the leptons, the neutrinos are stable. They have no charge, they have no mass, and their symbol is the gamma symbol. The tau or muon are unstable, and they are bigger than electron, but they actually decay into electrons or positrons. So they have more stuff that makes them bigger than the electron, but eventually they decay into the electron or the anti-electron anyway. The energy is released during these decays, just like in a radioactive decay. Now, when we have our chart of our subatomic particles, we have matter at the top. We have the hadron and the leptons below that. The hadrons are broken up into baryons and the mesons. And the baryons have 3 quarks made up of them, and the meson has a quark and an antiquark. Now, what you'll be asked to do is be given a certain amount of quarks that make up a particle, and will you be able to fit it inside this classification? So basically, you're working backwards to classify something that you may not know about in the first place. This is very similar to the taxonomic key that you learned about in biology, where you're fitting an unknown plant into what classification it has, or maybe an unknown insect or an unknown animal. Either way, the level of questioning that you'll be asked for in a state assessment is quite low, but this chart allows us to fit the particles that we may not have learned about, and I can't discuss all of them here. Where does it fit inside this chart? If it's inside the nucleus, it's got to be a hadron. If it's outside, it has to be a lepton. And if it's a hadron, is it made up of 3 quarks? If so, it's a baryon. If it's a quark and an antiquark, it's a meson. Now, like I said before, antiparticles exist. Every particle has an antiparticle, which is antimatter. The symbol is the bar over top of the original symbol. So electrons have positrons. So instead of an E with a negative sign, it's an E with a positive sign. A neutron has an antineutron. Instead of an N, it's an N with a bar over it. The proton has an antiproton. Instead of a P, it's a P with a bar over it. They're the same size, but just opposite charge. So each particle has an antiparticle component. So it's almost like how you have Superman and Bizarro Superman. Superman's the good guy. Bizarro Superman, he's a bad version of Superman. It's like Spider-Man and the dark version of Spider-Man himself. So there's, that's a terrible analogy, of course, but particles in the real world have antiparticles that go along with them. Now, when particles and antiparticles interact, they annihilate each other. So particles and antiparticles can come together, they explode and release energy. So that's when matter releases energy. And we can figure out the amount of energy released if we know the mass of them using E equals mc squared. On the other hand, if we know the energy that we have, we can produce matter from that. But you have to produce a particle and an antiparticle. So when you have gamma radiation, you can produce a particle-antiparticle pair, and we call that pair production. When you have a particle and an antiparticle collide, you produce energy, and we produce gamma radiation from that. So you can either produce energy from matter or produce matter from energy. And once again, this is all cutting-edge science. We're still learning about it today. This is something that, for an introductory physics course, may be a little bit on the verge of being too advanced. But what you're responsible for knowing is, if I give you 2 masses of a particle and an antiparticle, and they produce energy, can you multiply the 2 times the mass by c squared, by the speed of light squared? If so, you can figure out the energy in joules. And if the answers are in electron volts, can you convert to electron volts? Well, you need to divide by 1.6 times 10 to the negative 19 joules. The level of difficulty for the types of problems for the modern physics section is going to be fairly basic. You're going to need to know how to read the chart, and you're going to need to know how to deal with matter that you may not know about originally and place it within this taxonomic key, which we classify matter into. Finally, if you're given a number of quarks or antiquarks, can you use the chart's values for the quarks or the opposite sign of the values for antiquarks? If so, you'll be set for any question you can be asked. I have seen questions asked every year that are even unique, that are new every year. This isn't like kinematics where the same types of questions have been asked for hundreds of years. In fact, since this is new stuff, they come up with new questions based on some of the findings that they had during this year. So on a state assessment, you may be reading a passage from a research paper that was released this year or maybe the previous year. So as we get further along with modern physics, we're realizing that all you're responsible for knowing how to do is manipulate signs of charges, negate the sign if it's an antiparticle, and if energy releases to form matter, it's going to release and form two particles that shoot off in opposite directions because of conservation momentum. You had no momentum to begin with, and now these particles shoot off in opposite directions. Or if you have two particles that come together, can you figure out the energy that is created when they annihilate one another? At this point, we're done for today. We'll do a couple of sample problems dealing with these types of questions that can be asked. Otherwise, we'll take out the whiteboard now and solve some sample problems. Thank you. All right. Now the reference table classifies matter in a flowchart, and we have matter here. And it's broken down into two sections. We have the hadrons and the leptons. And the hadrons are in the nucleus, and the leptons are outside. So questions on the regents or other state assessments will deal with things as simple as this at first. If you have a hadron, is it affected by nuclear forces? Well, yes. Are the leptons? Not directly. It could be because of attraction or repulsion, but in terms of the strong or weak nuclear force, hadrons are the ones that deal with that. Now we have an entire chart for leptons, which we'll discuss momentarily, but then hadrons are broken down into two more sections. We have the baryons, and we have the mesons. And these are different types of nuclear particles that have different characteristics in terms of their structure. Now the baryons are made of 3 quarks. And that completes this leg of the chart. Now that means a proton, which lives in the nucleus, or a neutron, which lives in the nucleus, are types of baryons. Remember we discussed that the proton was an up-down quark. So that is made of 3 quarks. That's a baryon. So questions like that could come up as well. We have to be able to read this chart and understand what particles fit in the different spots. Mesons, on the other hand, are made up of a quark and an antiquark. Now, as we discussed in the lecture section of this day, the quarks and antiquarks, well, we have matter and we have antimatter. And the antimatter is similar in structure to the matter but has an opposite charge. So an antiquark we would use, for example, if we had an anti-up, which doesn't necessarily mean it's a down. And the reason that's the case is because the up was plus 2/3. The anti-up would be minus 2/3 of an elementary charge. A down was negative 1/3. So it isn't the same as an anti-up. But the antiquark we're going to denote with a line over it, a bar over it, and that's going to represent antimatter. Now matter and antimatter don't really like each other, and if they combine, they are going to annihilate one another. So we have the annihilation of matter when matter and antimatter collide. Well, using our E equals mc squared equation, Einstein's famous equation here, what we can do is figure out the energy released. If we know the mass of the different quarks and antiquarks, or proton and antiprotons, or whatever matter we have, If we know the mass of the two particles, we can add them together. And when they annihilate each other, they form energy. On the other hand, we can have energy create matter. We usually call that pair production. And if we have gamma radiation, we're going to know the energy. If they tell you the frequency, you may have to do E equals HF first. But once you do E equals HF, you know this E, and you can figure out the mass of the matter that's produced. Now, typically when matter is produced, if we have light rays coming in, forming matter, we're going to have one go in one direction and the other go in the other direction because of conservation momentum. But that would be a pair production. If we have matter, we'll just say plus and then plus with the bar over it, they come together, proton, antiproton, and they collide, well, they're going to annihilate one another and form energy. So you can either have gamma radiation form matter or matter form radiation itself. But the big trick for most of these problems is that the mass is the combination of the two. You'd have to take the proton mass and add it to another mass of a proton, although it's an antiproton. The anti being that it has a negative charge. But it's not an electron, because electrons and protons have completely different masses. So this is the first chart that we deal with on the reference table. We have the hadrons, which are either baryons or mesons. Baryons are made of 3 quarks. Mesons are made of quarks and antiquarks. And typically you'd be asked to find what's the charge of a meson if it has an up and a anti-strange or something to that effect. In that case, if we had an up and an anti-strange, well, the up has a charge of plus 2/3. The anti-strange has a plus 1/3. So the total charge will be plus 1. So a meson made up of an up and an anti-strange has a charge of plus 1. The negative 1/3 for the strange becomes a positive 1/3 because of the anti-particle. Next, we'll discuss the different types of leptons. All right, the final chart on the reference table lists the different types of leptons. And if you remember, the leptons were outside the nucleus. And the different types that are listed are the electron, which is the symbol E and has a charge of -1 elementary charges. The muon, which is a mu, symbol mu, Greek letter, -1 elementary charge. And the tau, which is the Greek symbol tau, and -1 elementary charge. Then we have different types of neutrinos. We have the electron neutrino, and the neutrino uses the symbol in Greek for nu for neutrino. And it looks like a V. It's got a little fancy section over here, but effectively looks like a V, and we use a subscript for each of the types. Neutrinos have no charge and no mass. And they were only recently discovered within the last 40 or 50 years. The other one is the muon neutrino. Oh, and of course it has no charge, so it's 0 charge. The muon neutrino is the mu, and has no charge, and the tau neutrino. And of course it's the nu and the tau, and it has no charge as well. And basically this chart, what we need to worry about is what is the charge, and for modern physics questions on a state assessment, they may give you an anti-muon or an anti-tau with a bar over it, meaning it has a +1 elementary charge or a +1. We can even have an anti-electron, which we call a positron, and that has a +1 charge as well. The neutrinos, though, anti-neutrinos, still have no charge because the opposite of the 0 is still 0. But this is our chart for leptons, and you need to realize that they're not affected by the nuclear forces. If we have a bar over a symbol, it means take the charge and negate it. So a negative becomes a positive, and a positive becomes a negative. But with the quarks and the leptons and the classification of matter charts, that rounds out our modern physics discussion. What you'll be asked to do is look at the chart and try to determine charges or whether or not a certain particle fits in a certain classification. Almost like you did in biology, where you had to figure out where a specific plant or animal fit within a taxonomic key. And that's it for leptons. All right, when particles and antiparticles interact, we can either create energy or we can create matter from energy. If we go from gamma radiation to creating matter, we produce pair production, is what we call it. So the gamma radiation has a certain amount of energy, and the pair that will be produced will have a certain amount of mass, and that mass will be split up between the two. We'll have a particle, and we'll have an antiparticle. One will go one way, and the other will go the other way. And typically, the light will come in, and then because of conservation of momentum in two dimensions, we have the particle and antiparticle flying off in opposite directions. On the other hand, we can have matter collide with antimatter, and that's going to form energy. And it could be gamma radiation or something else, depending upon the frequency. Remember, gamma rays have high energy because of their frequency value. But if you have matter and antimatter, you can create energy. So the matter comes in, collides with antimatter, and then the result is energy. And we call that annihilation. So they annihilate each other because antimatter and matter don't really like each other. But once again, if you knew the mass of each, you would do E equals mc squared. Add the masses together, so m1 plus m2, that would be our total mass. And we could do E equals mc squared to find the total energy. Now, different problems may list a proton and an antiproton, or a proton and an antineutron, or something like that colliding. Problems can talk about certain types of light that produces a pair of matter and antimatter. And what you'll need to do is possibly figure out the energy of the radiation doing E equals hf, or add the masses together and then do E equals mc squared. And if you know the energy of the gamma radiation, you can find the mass, and then divide by 2 to find the mass of each particle. So think of each of these modern physics questions as a puzzle. You're given part of the pieces of the puzzle. You have to figure out the unknowns. But remember, our equations for this section typically are E equals hf, or hc over lambda, E equals mc squared. And at this point, those equations should seem easy to you after we've dealt with some ones that were much more complex. So particles and antiparticles either produce a pair of matter and antimatter or annihilate one another and form energy. And E equals mc squared is the bridge between the two, c being the speed of light.